The electrician and the inspector had incorrect interpretations of the National Electrical Code. The correct method to calculate the size of the equipment bonding jumper for parallel service conduits involves several steps. Firstly, determine the total circular mils, abbreviated as cm, of all the phase conductors in each conduit. In this case, with 350 cm conductors per conduit, that equates to 3 times 350, which equals 1050 cm per conduit. Secondly, total the cm values for all conduits. With 4 conduits, this is calculated as 4 times 1050 cm, which equals 4200 cm. Thirdly, multiply the total cm by 12.5% to determine the required cm of the bonding jumper. This results in 4200 cm times 12.5%, which equals 525 cm. Refer to Table 250.66 in the National Electrical Code to determine the appropriate bonding jumper size. In this case, a 1/0 copper bonding jumper would be required. The grounding electrode conductor sizing requirement in Note 1 to Table 250.66 is only applicable for single conductors. For parallel conductors, you need to consider the combined cm of all conductors of the same phase. In this case, with 350 cm conductors per phase, that is 3 times 350 cm, which equals 1050 cm per phase. Next, total the cm values for all phases. Assuming 3 phases, this would be 3 times 1050 cm, which equals 3150 cm. Refer to Table 250.66 to determine the appropriate grounding electrode conductor size. In this case, a 2/0 copper grounding electrode conductor would be required. Rigid conduits are considered equipment when they contain electrical conductors. Therefore, they must be bonded together in accordance with National Electrical Code Article 250. A separate bonding wire must be run to each conduit. In this case, 4 1/0 copper bonding jumpers would be used to bond the service conduits together. The correct sizing of the equipment bonding jumper and grounding electrode conductor is critical for ensuring proper electrical safety. The electrician should verify the equipment bonding jumper and grounding electrode conductor sizes based on the calculations provided. Now let's delve a bit deeper into the intricacies of equipment grounding and bonding, especially in the context of parallel service conduits, referencing specific sections of the National Electrical Code. Grounding and bonding are fundamental concepts in electrical safety aimed at minimizing the risk of electric shock and ensuring the proper operation of overcurrent protective devices. The National Electrical Code, or NEC, provides comprehensive guidelines for these practices. When dealing with parallel service conduits, the equipment bonding jumper plays a crucial role. Its purpose is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of circuit breakers or fuses in the event of a ground fault. The initial approach taken by the electrician, summing the circular mils of the largest phase conductors in each conduit and applying this total to Table 250.66, is not the correct interpretation for parallel service conduits. Similarly, the inspector's method of multiplying the largest phase conductor of each set by 12.5% from 250.28D is also not the appropriate way to size the bonding jumper in this scenario. According to the NEC, and as previously stated, the correct method involves determining the total circular mils of the phase conductors within each individual conduit. This acknowledges the fact that each conduit is essentially acting as a separate raceway and needs its own bonding path. After calculating the circular mils for each conduit, these values are then summed to obtain the overall circular mil value, which is then used to determine the bonding jumper size. The 12.5% factor comes into play as a means to ensure that the bonding jumper is adequately sized to handle potential fault currents. This percentage is applied to the total circular mil area to derive the required circular mil area of the bonding jumper. Once the required circular mil area is determined, Table 250.66 is consulted to find the corresponding conductor size. Table 250.66 provides a direct relationship between the circular mil area of conductors and the required size of copper or aluminum bonding jumpers. Now let's consider the grounding electrode conductor, or GEC. The GEC connects the service equipment to the grounding electrode system, which could consist of ground rods, metal water pipes, or other approved grounding electrodes. The primary function of the GEC is to provide a path for fault current to flow to the earth, helping to stabilize the voltage to ground and further enhance the operation of overcurrent protective devices. Note 1 to Table 250.66, as mentioned earlier, is applicable only when dealing with a single set of conductors. In situations involving parallel conductors, the NEC mandates that the combined circular mill area of all conductors of the same phase be considered. This ensures that the GEC is sized appropriately to handle the total potential fault current from all parallel conductors. To clarify, the statement that rigid conduits are considered equipment and must be bonded according to NEC Article 250 is accurate. Article 250 outlines the requirements for grounding and bonding electrical systems to ensure safety. Section 250.92 specifically addresses the bonding of metal enclosures containing service conductors, affirming the need to bond the metal conduits. Furthermore, the requirement to run a separate bonding wire to each conduit in a parallel installation is a critical aspect of proper bonding. This is because each conduit needs its own dedicated low impedance path back to the grounded conductor at the service equipment. Simply connecting the conduits together in series with a single bonding jumper isn't sufficient and does not meet the intent of the NEC. By running a separate bonding jumper to each conduit, the impedance of the grounding path is minimized and the effectiveness of the overcurrent protective devices is maximized. In the specific scenario presented, with three 350 circular mill conductors in each of 4 conduits, a calculation of the equipment bonding jumper would proceed as follows. Firstly, calculate the circular mill area of the conductors in each conduit, which is 3 times 350, equaling 1050 circular mills. Secondly, sum the circular mill areas of all conduits, which is 4 times 1050, equaling 4200 circular mills. Thirdly, apply the 12.5% factor, which is 4,200 times 0.125, equaling 525 circular mills. Finally, refer to Table 250.66 to determine the appropriate conductor size. In this case, 525 circular mills corresponds to a 1/0 copper conductor. For the grounding electrode conductor, the calculation would be as follows. Firstly, calculate the circular mill area of the conductors of one phase, which is 3 times 350, equaling 1050 circular mills. Secondly, since we are dealing with parallel conductors, sum the circular mill areas of all phases, which is 3 times 1050, equaling 3150 circular mills. Thirdly, refer to Table 250.66 to determine the appropriate conductor size. In this case, 3150 circular mills corresponds to a 2/0 copper conductor. It is important to note that the NEC is a complex document, and its interpretation can sometimes be challenging. Consulting with a qualified electrical inspector or engineer is always recommended to ensure compliance and safety. Additionally, it is crucial to stay up to date with the latest edition of the NEC, as requirements can change over time. Now let's consider some additional aspects related to grounding and bonding in electrical systems. The concept of impedance is fundamental to understanding how grounding and bonding work. Impedance is the total opposition to the flow of alternating current in a circuit. It is comprised of resistance and reactance. Resistance is the opposition to current flow due to the material's properties, while reactance is the opposition to current flow due to capacitance or inductance. In grounding and bonding systems, low impedance is crucial. A low impedance path allows fault current to flow quickly and easily back to the source, which helps to ensure that overcurrent protective devices operate promptly. High impedance, on the other hand, can impede the flow of fault current, potentially delaying the operation of protective devices and increasing the risk of electrical shock or fire. Several factors can contribute to high impedance in grounding and bonding systems. These include loose connections, corroded conductors, long conductor lengths, and the use of improper materials. To minimize impedance, it is essential to use proper installation techniques, such as making sure all connections are tight and clean, using appropriately sized conductors, and avoiding unnecessary bends or loops in the conductors. Another important concept is the difference between grounding and bonding. Grounding refers to connecting the electrical system to the earth. This is typically accomplished by connecting the neutral conductor, the service equipment, to a grounding electrode system. Grounding helps to stabilize the voltage to ground and provides a path for fault current to flow to the earth. Bonding, on the other hand, refers to connecting all metal parts of the electrical system together to create a common electrical potential. This includes metal conduits, enclosures, equipment frames, and other metal components. Bonding helps to minimize the voltage difference between these metal parts, reducing the risk of electric shock. The NEC requires both grounding and bonding in electrical systems. Grounding is addressed in Article 250, Part Roman 2, while bonding is addressed in Article 250, Part B. It is important to understand the specific requirements for grounding and bonding in different types of electrical systems, as they can vary depending on the voltage, occupancy, and other factors. In addition to the general requirements for grounding and bonding, the NEC also includes specific requirements for certain types of equipment and systems. For example, Article 547 covers agricultural buildings, which have unique grounding and bonding requirements due to the presence of livestock and the potential for corrosive environments. Similarly, Article 550 covers mobile homes and recreational vehicles, which also have specific grounding and bonding requirements. When working on electrical systems, it is always important to consult the NEC and any other applicable codes or standards to ensure that the work is performed safely and correctly. Now, let's discuss some best practices for installing equipment bonding jumpers and grounding electrode conductors. Firstly, always use conductors that are appropriately sized for the application. As previously discussed, the NEC provides tables and formulas for determining the correct conductor size based on the circular melt area of the conductors being protected. Using conductors that are too small can result in excessive impedance and may not be able to safely carry the fault current. Secondly, make sure all connections are tight and clean. Loose or corroded connections can significantly increase impedance and reduce the effectiveness of the grounding and bonding system. Use appropriate connectors and tools to ensure that all connections are properly made. Thirdly, protect conductors from physical damage. Bonding jumpers and grounding electrode conductors should be installed in a way that protects them from damage, such as from impact, abrasion, or corrosion. This may involve using conduit sleeves or other protective measures. Fourthly, avoid unnecessary bends or loops in the conductors. Sharp bends or long loops can increase impedance and reduce the effectiveness of the grounding and bonding system. Keep conductors as straight and short as possible. Fifthly, use approved materials and equipment. Only use materials and equipment that are listed or labeled for the intended application. This helps to ensure that they meet the necessary safety standards. Sixthly, inspect the grounding and bonding system regularly. Periodically inspect the grounding and bonding system to ensure that all connections are tight and clean and that there are no signs of damage or corrosion. Address any issues promptly to maintain the integrity of the system. Seventhly, document the grounding and bonding system. Keep records of the grounding and bonding system, including conductor sizes, connection locations, and inspection dates. This documentation can be helpful for troubleshooting and maintenance purposes. Eighthly, follow the manufacturer's instructions. Always follow the manufacturer's instructions for installing and maintaining grounding and bonding equipment. This will help to ensure that the equipment is installed correctly and operates safely. Ninthly, stay up to date with the latest codes and standards. The NEC and other codes and standards are constantly evolving. Stay informed about the latest changes and updates to ensure that your work is compliant and safe. Tenthly, seek professional guidance when needed. If you are unsure about any aspect of grounding and bonding, consult with a qualified electrical inspector or engineer. They can provide expert guidance and help to ensure that your work is performed safely and correctly. Grounding and bonding are critical aspects of electrical safety. By understanding the principles of grounding and bonding, following the requirements of the NEC, and adhering to best practices, you can help to minimize the risk of electric shock and ensure the proper operation of electrical systems.